Here is a shape with a curved top, and we want the area underneath it. There is no neat formula for a region with a curved edge, so we do the honest thing and approximate. Slice the region into a few tall rectangles that follow the curve. Each one is easy, just height times width. Add up the areas of all the rectangles, and you get a rough estimate of the whole region. Rough because the flat tops overshoot here and undershoot there.
Those steps miss quite a bit of the curve.
They do, so here is the idea that fixes it, and it is the same idea as before, approaching a limit. Use more rectangles, each one thinner. The steps shrink, and the jagged tops hug the curve more closely. Thinner still and thinner again. In the limit, as the width of each slice goes to 0, the overshoot and the undershoot vanish, and the sum settles on one exact number. That number is the true area. That limiting sum has a name and a symbol. We call it the definite integral, and we write it with a long stretched letter S for sum. Read aloud, it is the integral of the function, from the left edge to the right edge. The stretched S remembers that underneath, it was only ever a sum of thin slices. Area is one face of the integral. Here is the other, and it is the one that connects back to last episode. Let the curve be a speed, how fast something is moving at each moment. Speed multiplied by a little slice of time gives a little bit of distance. Add up all those little distances, and you have recovered the total distance traveled. Watch it accumulate. As time moves forward, the area under the speed curve fills in, and the running total climbs right along with it. So the integral takes a rate and gives back the total that the rate built up. Last episode, the derivative pulled a rate out of a total. Here we are going the other way, and that is not a coincidence. Now, actually adding up 1,000 thin slices by hand would be miserable. So a natural question, is there a shortcut, a way to get that exact area without the endless sum? Here is the hunch that changes everything. Suppose we can find a function whose rate of change is exactly our curve. Call it the accumulator, the running total from the last scene. Its slope at every point is the height of our curve. If such a function exists, then the whole area might collapse into something almost embarrassingly simple, just the accumulator's value at the end minus its value at the start. A difference of two numbers instead of an infinite sum. That suspicion has a name, the fundamental theorem of calculus, and it is next. So the integral is accumulation. Sum many thin slices, take the limit as they thin to nothing, and you get an exact total, an area, a distance, an accumulated amount. The derivative breaks a total into its instantaneous rate. The integral gathers a rate back into a total. They look like opposite motions, and next episode we make that precise. The fundamental theorem shows they are two sides of one coin.